All right, so from 4.5, I want to go ahead and do question number 10 here. And we commented about this one last time. Do you remember this one? I think I had you all draw some soda cans, right? Same idea here. I guess in this case we've got oil coming in a 1 liter can. I don't think oil comes in cans anymore, but in the olden days it did, I guess. And it makes a nice math problem. So, what type of question is this? This is the first thing you should identify. Well, it says it's from 4.5 optimization problems. Okay, it's an optimization problem. How do you know that in reading the question? It says to minimize the amount of material. It says cost of metal, but if it's all the same metal, then that's the same thing as minimizing the amount of material. Okay? So this is an optimization problem. I'm asking you to find in this case, the smallest amount of material. Okay? Remember we talked about last time those EST words that show up in these types of problems. I'm asking you for the extremum. Okay. How do we do these problems? This is a recap more so of the process than how to do this one particular problem. How do we do these optimization problems? Draw a picture. Great, I like it. Let's draw a picture here. Okay? Here's an oil can. Okay? Let's label some dimensions. And by the way, when you draw a picture, don't just draw, a nice happy picture and draw a fun little label on it or something like that. Go ahead and put your variables on it too. What do you need to be able to describe this cylinder? All cylinders, this is called a right cylinder. All right cylinders can be described by just 2 numbers. What are those 2 numbers? Yeah, the radius and the height. Okay. You could also do diameter and height, but you need to somehow describe how big the circle is, which we usually do with radius, and you need to describe how tall the can is, which we do with height. Okay. Any questions on that? Okay, we're now going to build 2 different equations. The what and the what? What do we call them? What's that? The optimization function, and then we'll build also the constraint, right? If I said make a can of oil that's going to minimize the amount of material it takes to make it, why don't you make one really just about that one right there? Why didn't that work? Because it's got to hold a liter. That's my constraint, right? I'm constrained by the fact, in the process of minimizing the material, I'm constrained by the fact that it must hold a liter. Okay? So in fact, let's go ahead and say that we are constrained by the fact that the volume must equal 1 liter. Okay? How do we find the volume of a cylinder? I do expect you to know this. Yeah, how do we think? How do we think about that? The base of the circle, the base of this column times its height, and in this case, the base is a circle. Okay, so these are called prisms. In this case, I guess you'd call this maybe a circular prism. Okay, and for these prisms, you just take the underlying base and then cross it with a 3rd dimension. In this case, the height. Okay? So when I look at this, I just think of, I've got this circle right here, and I just stretch it up by a factor of h. That gives me a 3-dimensional object. So what's its volume? It is the area of the circle, pi r squared, crossed with the 3rd dimension. Area times height equals volume. So we get L. Oh, 1L. I want to say this, though. A liter is a perfectly fine measurement of volume, but it is itself just liters are raised to the 1st power. It's already a unit of volume. And I want to think of it as being a product of 3 dimensions. So what is a liter equivalent to? Yeah, a liter is equivalent to 1,000 cubic centimeters. If you don't know that, that's okay, I'm telling you. On a test question, I would go ahead and just say that this volume is 1,000. I won't mess with the units with you on a test question. Okay, but my math lab will at times, so we're practicing that. Okay. For those of you who don't know, 1 liter is equivalent to 1,000 milliliters. That part you should know. And then what is a milliliter? A milliliter is 1 cubic centimeter. So if a liter is 1,000 milliliters and a milliliter is a cubic centimeter, then a liter is 1,000 cubic centimeters. All right. So this is our constraint. And then MC said, oh, we've also got to come up with our objective function. The thing that we're being asked to optimize. What are we being asked to optimize here? What do you say, Haley?
We're asked to minimize the material or
material, or we could think of it as surface area, right? The material that comes up as a surface area. All right. When you do these problems about material, I recommend you think of trying to wrap a Christmas present, but not as you wrap one nicely. Think of how Mr. Von Toggen wraps his Christmas presents, because he's lousy at it. If I wanted to wrap this can, you know what I would do? I would cut out a circle, and I would glue it to the top. And then I would cut out a circle, and I would glue it to the bottom. And then I would cut out something to wrap around the side and glue it to it. Okay? That's how I want you to think of doing this. If you think of it that way, then you'll be able to come up with the formula for the surface area of a cylinder. That's, again, something I ask you, I think that that's fair to ask you to deconstruct that. I'll show you the process. Okay? So what did I say? I said, oh, I want, for the material, which will be a function of both R and H, I said, oh, I want one circle right here that I'm going to cut out and I'm going to glue to the top, right? That circle can be described by just the radius, right? And then I want one for the bottom, right? Then, at this point, what is still left to be wrapped? Oh, very good. Very good. Okay. Let's talk about that. I want to talk about that just a little bit more. At this point, I've taken care of the top and bottom of this can, so I'm left with a sort of a tube with no top and bottom. Okay. What could I think of doing? I could think of taking a scissor and cutting it along like that, right? And then in your head, if you could imagine, I cut along this tube and I unfold it. What type of shape do I get? I get a rectangle. Ooh, that's a little weird. I get a rectangle. Okay? And what do I know about this rectangle? Well, I cut along this dimension here, which was this line right here, so what's this dimension? It's H. And then, what do I have to do with this? I've got to wrap it around the circle. So as Amy said, how long is this?
Circumference.
It's the same as the circumference of the circle, right? How do you find the circumference of a circle? It's 2 pi r. Okay? Folks, I will not give you, if this question showed up on a test, I won't give you the formula for surface area. I won't give you the formula for volume. If you've dead forgotten, I'll give you the area. You come up to me and ask me, I'll give you the area for the formula for a circle. If you've forgotten circumference of a circle, I'll give you that. But from those two pieces, I expect you to be able to deconstruct this cylinder and then come up with the surface area formula. Stop thinking of formulas as these mystical expressions that somebody came up with. They're built from very basic principles most of the time. Okay? All right. So what is our surface area? It's going to be 2 pi r squared. What does that take into account? It takes into account this circle and this circle here, right? Plus, how do I find the area of this? What do you say, Chandler? How am I going to find the area of the tube part of the cylinder? Yep, exactly. Exactly. So what would it be? 2 pi r h. Great. Okay. There's our constraint problem. So what are we being asked to do here? Well, we're being asked to minimize the what? The material. So I need to come up with the material as just a single function, or excuse me, a function of a single variable, right? I can't do calculus on that expression because it's got too many variables. So what do I do? What's my next step? What do you say, Jigme?
You have to get rid of one of the variables.
Yeah, we got to eliminate one of the variables, and how do we usually do that? What do we usually go to? Go ahead. You go to the constraint function. So we're going to go to this expression right here. Okay. I don't know if you want to call it a function or equation, I don't know. But you're going to go to that constraint function or constraint equation right there, and you're going to solve for one of the variables. Sometimes in these problems there will be a best choice. Like if all you were ever after, if the problem said give the radius that will minimize the amount of material, then there's a clear choice. You definitely want to get rid of h. Or if it said find the height that will minimize the amount of material, then there's a clear choice. You want to get rid of r. So you'd solve for r. But when there's not a clear choice, you want to pick whichever one's easiest to solve for. Who's easiest to solve for in this problem?
We don't want a square root. So.
Yeah, I don't want to introduce a square root here, so let's go ahead and solve for h. So this gives us that h is equal to 1,000 over pi r squared, dividing this pi r squared over to the other side. So at long last, we can write the amount of material as just a function of one variable r. It would be 2 pi r squared plus 2 pi r times 1,000 over pi r squared, right? I can't remember. I got distracted by this symbol that showed up. Okay, great. I can take one more step to clean this up. And as we've always seen in this class, it's easier to clean up your functions before you do calculus with them. And that's our objective function, now written as a function of just one variable. Okay? So now that I've got this, what do I want to do? Now we're ready to do some calculus. This whole problem, this whole real-world problem of coming up with the dimensions so we use the least amount of material possible constructing this oil tin is really just a find the extreme values of this function problem. Specifically, we want to find the absolute minimum of this function. So let's go ahead and give that a shot. Okay. The smallest r could be is 0. So notice that this is, so let's say just minimize this. On the smallest r could be is 0. And technically, what's the largest r could be? It could become infinitely large because if you're going to have a volume, you can't derive it into it, but it can become as, you can make it as large as you want, because if you're going to have a fixed volume of a liter, you just make the height very, very tiny times whatever the size of your circular base is, and that ensures that you can still get to 1,000. Right? So you could still always get to 1,000. So there's no upper limit on what your radius could be for these cans. Okay, so we want to minimize it on this interval. So here we go. We take the derivative because we're looking for the critical numbers. So here's the derivative. It is 4 pi r minus 2,000 over r squared. We're missing adding. Any questions on how we did that? Anyone have any questions about that derivative? So I thought of this as 2,000 r to the minus 1 power, right? And then I did my power rule and put it right back down. Okay, any questions? Okay, so I set this equal to 0. Let's take the 2,000 r squared over to the other side. So we get 2,000 over r squared equals 4 pi r. Doggone it, an equation with fractions. Let's get rid of the fractions. We're powerful mathematicians. How do we get rid of fractions? By multiplying by the LCD. Right? So multiply both sides by r squared. We get 2,000 equals 4 pi r cubed. We can do that because r can't ever actually be 0. Divide both sides by 4 pi. We get that r cubed is equal to 500 over pi. Don't let your eyes glaze over. Don't pick on this number. It's going to be ugly. Okay? But it's the one we want. We get r is equal to the cube root of 500 over pi. Just to give us a dimensional, just to give us a sense of the size of that, if somebody would take the, give me a decimal approximation, was it 5.419? We'll call it 5.4. Just, I mean, that's fine. I like that you gave that far, but let's just leave it at 5.4. Just to give us a, 5.4 what? Centimeters, right? Just to give us a little bit of sense of size now. So whenever you see this ugly number here, if you want to think about them as 5.4, you can. What's that? Well, that's the radius, though, right? Not the diameter.
Oh, right, yeah.
Yeah. So that's a good size for a 1 liter oil can.
Yeah. 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 I mean,
Think about your Nalgene bottle. It's about a liter.
yeah. Yeah.
It's not the ideal size either, though, because they want you to hold it in your hand,
Yeah.
right? All right. All right. So that's our radius. Where we have a what? All we know so far is this is where we have a what? We don't even know it's an extremum. We don't know it's a min or a max. All we know is that it's a critical number, right? Now we only got one critical number, so we're feeling pretty comfortable, right? What do we need to do? All we need to do is confirm that it is a local minimum, and if it is, then it will also be the global minimum. So all I have to do is confirm that this is a local minimum. To do that, what do I have to do? What do you say? What do you say, Abby?
Wait, we're confirming that it's a local minimum.
Confirming that it's a local minimum. So we've got two possible things we could do. The first thing we could do is the first derivative test. What's the second one?
Second derivative?
We could do the second derivative test. Okay. Which one would you like to do? Yeah, hopefully you're learning that for these nasty story problems where the numbers aren't nice, it's a lot easier to do the second derivative test on them most of the time. Okay, so let's find the second derivative. M double prime of r should be 4 pi plus 4,000 over r cubed, I think. Let's check that. I can't remember. Yes, 4 pi r, so that'd be 4 pi. And then plus 4,000 over r cubed. Any questions on that? So how did I do that? I went back to the first derivative, and I just thought of this term right here. I thought of it as minus 2,000 r to the minus 2, and then I did my power rule on it, right? So I brought down the minus 2. That's how I got plus 4,000. Subtract 1 from it gives it minus 3. Take that minus r to the minus 3 down below the line. Okay? Now, we found the second derivative. Great. How do we actually apply the second derivative test? Yoshin, what should I do? So we found the second derivative.
We already find the second derivative.
Mm-hmm.
And just make sure they are like less than 0.
Yeah, so we're looking, well, actually, because we're looking for a global minimum, we're actually hoping that it's going to be greater than 0 because we want it to be concave up, right? So how do we check that? We simply take our critical number right here and plug it in, right? Well, we get m double prime of the cube root of 500 over pi. Well, what's the sign on that? Don't work too hard, folks. 500 is positive, pi is positive, so their ratio is positive, so their cube root is positive, so I'm plugging a positive number in for r. This whole expression is going to be positive. Notice that's the beauty of doing the second derivative test on these story problems. Generally, it doesn't require much of an argumentation to show what the sign of the second derivative is. Okay. Why did I check for the sign of the second derivative? What's the logic there? What do you say, Kasha?
To find the minimum,
How does that tell us it's a minimum?
because it's a local minimum, therefore a global minimum.
That's true. You're doing the last two steps, but I'm missing a step in between there. How do we know that that's a local minimum?
Because if it's greater than 0, it's concave up.
If the second, so let's be a little careful with our pronouns. if the second derivative is positive, then we know that it's concave up. But what did we also know about this r value? So we know this tells me that it's concave up on the function right there. But there's lots of places along this concave up interval that we could be talking about, right? How do I know that it's the minimum of that interval?
That's where the first derivative is.
Yeah, we set the first derivative to be 0 there when we found that r value. So we also know that it is a place where we have a horizontal tangent line. So while there are many potential places on a function that it could be concave down, there's only one place where you are concave down and have a horizontal tangent line. And where is that? Right there. So it is indeed, you don't have to worry about writing that out, but that's what the second derivative test is telling you. That's why to do the second derivative test, you find a place where the first derivative is 0, and then just check its concavity. And as long as that concavity is not 0, you can make a conclusion. Okay. So, oh yeah, Haley.
This is just kind of like a general question.
Uh-huh.
Like, what would be the best, like, kind of question, I guess, in your opinion, that would work for, like, the first derivative test?
Yeah, that's a great, yeah, that's a really good question. So we have these two derivative tests. Why did I give you 2? Just give you more things to juggle because you don't have enough. No, that's not the answer. Okay. Why did we give you 2? Well, different ones are applicable to different scenarios. I find that when it comes to graphing the entire function, I like to do the first derivative test in the chart that we do because that helps me with graphing the rest of the function. It gives me the intervals for increasing, decreasing, besides telling me whether I've got a local max or local min at a point. Okay. But for the second derivative test, I find that that's faster when I just want to know about one bit of information, just what is going on at this one point. It's usually faster to check with the second derivative. So the short answer is, when I'm doing my graphing problems, I usually use the first derivative test. When I'm doing my story problems, I generally use the second derivative test. That's not quite, I don't know if that's a hard and fast rule, but that's generally what I do. Yeah, great question. Great strategy question. All right. Okay, so r equals the cube root of 500 over m, or excuse me, 500 over pi, is a local min. That's far enough for me. That's all you have to tell me. Okay? Just to reiterate, there's some more explanation going on here. Okay? The additional explanation is, since it was the only local extrema on 0 to infinity, it's also the global min on its domain. That's the extra step that tells us that we've actually found the global min. I don't require you to write out a statement like that. I feel like it's just a little bit too complicated. And if you've gotten to that point in the story problem, I'm satisfied. Okay? But what do you have to do? You can't just find a critical number and call it the answer. You do have to show that it's a local of whatever it was I told you to find. I do require you to pay lip service to that. Okay? To be honest, folks, if you take the second derivative like I did, and then you plug in the number, then just write out, to be honest, just write out whatever that's, just write out what that's supposed to be. You know you're looking for a local minimum, so you know it needs to be concave up, so just put greater than 0. I won't know that you didn't actually check it. Right?
We don't have to put the, like, what that equals?
Well, I mean, you don't actually have to find, I don't require you to find the number, right? I don't ask you to find the value of the concavity. I just ask that you check the sign on it. But if I'm asking you to find a global minimum, it's going to be a problem that has a global minimum to it. So it's going to have the local minimum at that location. So this is never not going to be what it's supposed to be. I don't do that to you. The only problem where you saw where this didn't happen was that wire problem that we did at the very beginning. Okay? And that was when we looked for the maximum for the wire, the square was best, which was at one of the endpoints. All right. All right. So did we ATFQ, did we answer the question? No, what was the question?
Dimensions.
Give the dimensions, right? Okay. So we found the R value. We found the R value that's going to give us the global minimum, but what else do we need? The height. Boy. Oops, I didn't do it here. Where is it? Boy, I sure wish I had an equation for H in terms of R. Boy, I sure wish I had an equation for H in terms of R. Oh, I will have always done that in the process of solving for the constraint, right? Okay, so let's see, 1,000 over pi r squared. Oops. So we get that H is equal to 1,000 over pi times the cube root of 500 over pi squared. If you want, you could get a decimal approximation of that, but it's not required. There's the exact answer. I'm satisfied with parking it there, except for what? We should probably put centimeters on here and centimeters on there. Did we find the two dimensions? Yes. We've answered the question. Okay. Now, it could be on a problem like this, I might say in the question, I might say, what is the minimum surface area? That'd be kind of mean for this one just because the numbers are so nasty. But what would you do in that case? You would actually take your M, your R, and your H, and you would go back to here and evaluate and figure out what is that minimum surface area. I'm saying that just because two questions can look pretty doggone similar, but what I'm asking for the final answer is slightly different in them. Okay, there's that. Okay. So there is, you will have a video up shortly. Let's see, we did this one in class. You'll have a video up shortly that does these two, number 16 and 17. Okay, actually the video's already up for that. You could already watch the video on that. I'm going to make a new video that puts all these together. But the video's already up for how to do 16 and 17. Okay. So I would watch that, because those are definitely fair game questions here. All right. I want to now jump back to section 4.9. Do I have it? I guess I don't have it yet. Let's stop this.